Assalamualaikum to Madam Nur Farhana. My name is Hani Nadira binti Nur Jeffrey, and today I'm going to present about application logic in real life. So first thing first, logic is the invisible engine of human thought, guiding everything from our simplest daily choices to our most complex long-term plans. It serves as our cognitive framework for making judgment, weighing evidence, and drawing the conclusions necessary to solve problems and make sound decisions. Today, this ancient human tool has evolved into the literal DNA of modern technology, particularly within computer science, by translating our natural reasoning into simple structured formulas, specifically conditional if-then statement, mathematically expressed as P implies Q. We are able to teach machines how to think. We see this in action every day. If you enter the correct PIN, then the ATM dispenses cash. If a traffic timer expires, then the light turns red. If a password matches the database, then access is granted. Ultimately, by reducing unpredictable real-world scenarios into these unbreakable logical rules, logic acts as the bridge between human intellect and engineering, allowing us to build smart, automated systems that make safe, predictable choices for society. Next, I'm going to present about conditional statement. In computer science, systems make decisions using conditional statement, also known as implication. This concept allows a program to execute different blocks of code based on whether a condition is true or false. The core structure is written as P implies Q, where P is the premise or the condition and Q is the conclusion, the outcome. This relationship is only false when P is true but Q is false. In other scenario, it remains true. You can express this relationship in a few different ways, such as if P then Q, P implies Q, or Q when P. Through this simple logic, we enable computers to make smart and safe choices. Building on basic conditional logic, we can create new related statements by flipping or negating our original premise and conclusion. If our starting statement is if P then Q, for example, if Adam learns Python, then he will build a mobile app. We can manipulate it in three distinct ways. First, by swapping the positions of P and Q, we get the converse statement, P implies Q. If he builds a mobile app, then Adam learns Python. Second, if we negate both parts without changing their order, we can create the inverse, not P implies not Q. If Adam does not learn Python, then he will not build a mobile app. Finally, if we both swap and negate them, we get the contrapositive, not Q implies not P. If he does not build a mobile app, then Adam does not learn Python. Last but not least, beyond this variation, logic also allows us to link two propositions even more tightly using a biconditional statement. Represented as P biconditional Q, this creates a two-way street often read as P if and only if Q, P if Q or if P then Q, and conversely. Unlike a standard conditional statement, a biconditional proposition operates on strict mutual agreement. It is true only when both P and Q share the exact same truth value, meaning they are either both true or both false together. If one is true and the other is false, the entire biconditional statement breaks down and becomes false. Mastering these advanced structures gives us the precise framework needed to handle complex, interdependent relationships in both advanced mathematics and computing systems.
Hi and Assalamualaikum. My name is Kasrina Mardia and I'll be explaining about truth tables. So basically, a statement can be separated into two, which is true or false. For example, Kasrina is sleeping, which is false. Next, Kasrina is recording a video. That is true because I am recording a video right now. Besides, as you can see on the slide, there are logical operators that use to connect a statement. Without further ado, let's see the real-life scenario to make sure we truly understand the use of truth table. Statement 1. If the phone is on low battery, then the screen is bright. The phone will off automatically. First, we need to separate the statement by statement to a variable. The first statement, if the phone is on low battery as variable P, the screen is bright as variable Q, and the phone will off automatically as variable R. Next, we need to connect the statement using variable and logical operators. So, as we know, if the statement have a condition which is if then, we need to use implication. Then, if there's a full stop on the statement, we need to use conjunction. So, the result is P implies Q and R. For statement 2, we make a negative statement of statement 1. So, the statement sounds like this. If the phone is not on low battery, then the screen is not bright. The phone will not off automatically. Same as before, we just make the variable as negation P, negation Q, and negation R. To clearly see the difference, let's see the truth table. As there are 3 variables, we need to put the 4 column of P as true and the rest as false. Next, for Q, we put 2 column of true and next 2 column of false alternately. Then, P implies Q. If P is true and Q is false, then the result is false. Other than that, the result will be true. Next, R is alternate of true and false. For final result, we look at P implies Q and R. If P implies Q is true and R is true, so the result is true. Other than that, it's false. Next, for negation P, we just switch the true of P to false, then the step is just the same with before. In conclusion, the two statements are not logically equivalent because they doesn't have similar truth tables. Next is argument. Argument is a set of 2 or more sentences that intended to provide support or evidence for others. One of the sentences is the conclusion, while the rest are premises. If you don't understand, don't worry. I'm going to explain to you the real-life scenario. The server is running a new update. If the server is running a new update, then the system firewall is active. The local backup drive is full or the security protocol is verified. If the security protocol is verified, then the system firewall is not active. Therefore, the local backup drive is full or the network status is marked as secure. So, the server is running a new update. We put as variable A, the system firewall is active as variable B, the local backup drive is full as variable C, the security protocol is verified as variable D, and lastly, the network status is marked as secure as variable E. Then, we need to connect the statements using logical operators and the result is shown on the slide. Next, for rules of inference, we need to make a table like this and write the statement as premise 1 until premise 4. The conclusion doesn't include it. So, for the first step, we want to eliminate A. So, we use modus ponens rule and the result we get is B. For step 2, we want to eliminate B. So, we use modus tollens rule and the result is negation D. Next, we eliminate D using disjunctive syllogism rule and the result is C. Lastly, we use addition to add E, so the final result is C or E, which is matched with the conclusion of the statements.
As for conditional and biconditional, there are 3 new statements that will make some changes in the main conditional. Those are called inverse, converse, and also contrapositive. If the original statement is called P implies Q, then as for inverse, it will be called negation P implies with negation Q. As for converse, it will become Q implies with P. And for the last one, contrapositive, it will become negation Q implies with negation P. The example statements will be, if Akira buy a bungalow, then she will not buy a car. There are 2 statements there, which is statements P and statements Q. As for statement P, it will be if Akira buy a bungalow. And for the statement Q, it will be Akira does not buy a car. Moving on to the example for inverse. The inverse statements will negation P implies with negation Q. Thus, the statements will be, if Akira does not buy a bungalow, then Akira will buy a car. As for the second conditional statements will be converse. Converse statements will become Q implies with P, which will produce, if Akira does not buy a car, then she will buy a bungalow. Moving on to the third statements, which is contrapositive statements will become negation Q implies with negation P. Thus, the full statements will become If Akira buy a car, then she will not buy a bungalow. These are the few examples for conditional statements. As for the second part is the truth table. This truth table is to determine whether the two statements are logically equivalent or not. There are two examples I provided here. The first statement is logically equivalent. As you can see, first statement and the second statement is the same. Thus, the result of example 1 is logically equivalent. Moving on to the second statement. As for the second statement, as you can see for the both results, these are not logically equivalent because the result of both sides is not the same. Thus, the result of example 2 is not logically equivalent.
Hi everyone, today I'll be presenting section 3.3 Argument and Rules of Inference. Let's start with a real life scenario. If I buy a new laptop, then I will install antivirus software. If I install antivirus software, then my computer will be secure. But in this case, my computer is not secure. We can represent this situation using propositions. P, I buy a new laptop. Q, I install antivirus software. R, my computer is secure. From this, we form the premises. First premise, P implies Q. Second premise, Q implies R. And third premise, negation of R. Now, let's apply the rules of inference. From premise 1 and 2, we use hypothetical syllogism to get P implies R. Then combining P implies R with negation of R, we apply modus tollens. This gives us negation of P. So the conclusion is, I did not buy a new laptop. This example shows how logical reasoning works step by step. By applying rules like hypothetical syllogism and modus tollens, we can move from premises to a valid conclusion. That's the essence of arguments and rules of inference. They help us prove statements logically and avoid faulty reasoning.